Greetings. Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 16. Today we will continue to look at the bipolar transistor and try to develop a model for it, a circuit model that we can use in our analysis and design. What we have seen so far is that the bipolar transistor has some sort of exponential dependence between its base emitter voltage and its collector current. Now we would like to formalize this behavior and represent it by more familiar devices such as current sources, resistors, maybe diodes, that sort of thing, so that we don't have to think of the bipolar transistor as some strange device. So before we go there, let's just remember what we did last time. So in the previous lecture, we tried to build a little amplifier using a bipolar transistor, and we noticed that if we apply the microphone signal directly to the base emitter voltage, then the current that we generate is extremely small because we are over here in the IV characteristic. So that's not very good, and we played a trick. We said, what if we superimpose this microphone voltage on a DC value that is provided by a battery? So now we are not operating here anymore, we are operating here. So when there is no signal from the microphone, the base emitter voltage is a certain amount and the current is a certain amount. And when the signal comes in, we increase, for example, or decrease the base emitter voltage by some amount, and we create a current change. And that current change is much larger than the current change that we had originally with no DC here. And that's what we call biasing. So in the absence of a signal, we have applied something to bias the transistor, meaning we have a non-zero base emitter voltage and a non-zero collector current, even though there is no signal. We are over here. And when the signal comes in, we perturb this point this way for the base emitter voltage and this way for the collector current. So this biasing scheme is important in our design because we know that without any bias, the transistor is more or less dead and it doesn't have any amplification. Now, one other concept that we came up with was transconductance. We saw that if we bias the transistor here, then for a certain microphone signal, let's say 10 millivolts, we get a certain amount of current change in the collector, and as a result, some voltage at the output. But now, if we change the operating point to a higher base emitter voltage, so we use a larger battery voltage and a higher collector current, then we see that the microphone signal gives us a greater current change and hence a greater output voltage. So the circuit has more amplification. And to quantify that effect, to represent that effect, we said, why don't we look at the slope of the characteristic? Here we have a lower slope, here we have a higher slope, because this is an exponential function. So we defined the slope of this characteristic, IC versus VBE, to be the transconductance of the device. If the device is biased here and it has a certain current, let's say 1 milliamp, then it has a certain transconductance. And if it's biased here, it has a higher amount of current, so it has a higher transconductance. The transconductance of a bipolar device tells us how much the bipolar device translates a voltage change to a current change, how strong or how sensitive it is. When we change the base emitter voltage by some small amount, like so, how much change in the collector current we get. That shows the strength of the device, and that's why we call it transconductance. The unit of transconductance is 1/ohm or Siemens. Also, we remember that the equation we derived after this differentiation was just this, IC over VT. So that's the equation that we will be using quite often. It just says that to find the transconductance, we find the bias current, and divide it by VT, 26 millivolts. That will give us what we need. All right, so today we will start from there, and we summarize the IV characteristics of the bipolar transistor just to make sure that everything is clear and on one page. Then, based on these observations, we try to construct a simple model for the transistor. As I said, a model that's based on more familiar devices so that we can use it to analyze circuits. And then from here, we naturally enter this type of distinction between large signal operation and small signal operation. We have to see what that means, why it is a big deal, and why we need to make that distinction. All right, so let's begin with a summary of the IV characteristics of bipolar devices. So, IV characteristics. So this is nothing strange. We have seen these characteristics a number of times. I've just decided to summarize them here. So we have IC versus VBE, and it's an exponential function. In this test, we are varying the base emitter voltage, but the collector emitter voltage is constant. And remember that this model is valid only in the forward active region, meaning that the base emitter is forward biased and the collector base junction is reverse biased, or maybe it has zero bias on it. It is not forward biased. Okay, another characteristic that we had was IC as a function of VCE. And we saw that for a given base emitter voltage, the collector current is constant. It doesn't depend on VCE. So if we take a bipolar transistor and perform these tests on it, so we have two batteries, one for VCE, one for VBE. And in these two tests, we have different experiments. On the left, we keep the collector emitter voltage constant, and we vary this, and we see an exponential rise in IC. In this test, we keep the base emitter voltage constant, and we change the collector voltage, collector emitter voltage, and we don't see any change, at least not at this point. Because we were thinking that the current that flows from emitter to base is really defined by the base emitter junction and shouldn't depend much on what's happening on the collector side. All right, so because this is a flat line, we can conclude that this device operates as a current source. That is the definition of current source we remember from basic circuits. A current source is a device that maintains a constant current regardless of the voltage across it. So if I consider this as a two-terminal device, put all of this in a box, I see that even though this voltage is varying, the current that this device draws does not vary. So it qualifies as a current source. But it's also a voltage-dependent current source, because if I change this internal voltage from one value to another value, so from VBE1 to VBE2, then I get a new current source. Here I have a 1 milliamp current source. Here I have, for example, a 2 milliamp current source. So in each case it's a current source, but it has different values. All right, so based on these observations, we can try to develop a simple model for the transistor that we can use in analysis and design. Now, before we go there, I wanted to mention one more point that will help us greatly in our modeling and analysis later. And that is related to the concept of combining time response with IV characteristics. So let's see what that means. Well, we saw in our examples when we had a microphone here that the microphone creates a certain change on the base emitter voltage, in the base emitter voltage. So here's what we have as an example. We have a VCE here. We have our microphone signal here. And then we have another voltage here, which we might call V1 or V0 or something. And then the base emitter voltage is here. And we are examining, for example, the collector current, IC, which flows this way. So what we saw was that the relationship between IC and VBE is like this. The relationship between IC and VCE is like this. But in this case, the base emitter voltage is also changing with time because the microphone signal is changing with time. All right, so let's try to plot VBE as a function of time. So VBE as a function of time looks like this. We have a bias value for VBE equal to V0, meaning when there's no signal, VBE is equal to V0. So that would be our bias value. So we'll plot it like this. We call it V0. This as a function of time. Now, when the signal from the microphone arrives, we go up and down around this value. So something like this, right? So that is the base emitter voltage as a function of time. Now, I have the base emitter voltage as a function of time. I have IC as a function of VBE. So how do I find IC as a function of time? Because if the base emitter voltage is changing as a function of time due to the microphone signal, I am also interested to see how the collector current changes as a function of time. So I would like to combine this plot and this plot, right? So here's a nice way of doing that. We draw IC as a function of VBE. So that's just our good old exponential. So here's our exponential. Now we take this plot of VBE as a function of t and rotate it clockwise by 90 degrees so that this VBE axis is aligned with this VBE axis. And this time axis is pointing downward. So here's the time axis, here's the VBE axis, and this is here. So we have V0, and then around it we have the fluctuations due to the microphone signal. So this amount is V0. Okay, so as the microphone signal comes in, it says we start from V0 and we go up, we come down. We go up, we come down. We go up, we come down. So we are just changing the VB around this value. And due to that, we are also changing the collector current. So, for example, if the microphone signal has raised VBE to this much, then we can find the collector current, right? That's the collector current. And if the microphone signal has reduced the VBE to this much, then we can also find the collector current. So now I will construct another plane here, and I will call that IC as a function of time. And I perform this mapping operation. I say this point on VBE, this is the VBE axis, right? This point on VBE maps to this current in the collector. So I will take this current and plot it here, 1 point. Then I say, for example, this point on VBE maps to this current. So that would be another one. And so on, and then we connect all of them, and that's our collector current as a function of time. We know that in the absence of a microphone signal, base emitter is only V0. So if that's only V0, then the collector current is some amount, right? It's the bias value. So we will call that bias value something just to remember it. So the bias value we might call IC0 or anything you want. Not a big deal. Okay, so the bias value is in the middle of this approximately, and its value is equal to IC0. So combining the base emitter versus time plane with the IC versus VBE plane allowed us to plot IC as a function of time. It's pretty simple, but very intuitive and very clear in what you should expect. All right, one last question about this before we move on. If this microphone signal is a sinusoid, is this a sinusoid? Well, no, not necessarily. You can see that we have a nonlinear function here. We are subjecting a sinusoid to this nonlinear variation. So whether this is a sinusoid or not, we don't know, probably not. So that's an interesting point that we will come back to a little later. All right, so with that, we are now ready to look at the simple bipolar transistor model. So simple bipolar transistor model. Okay, well, what we do know is that the collector current as a function of the base emitter voltage is an exponential. So we decided that it's a current source and it's a voltage dependent current source. So I will draw a current source between the collector terminal and the emitter terminal, and I write it as IS exp of VBE over VT, assuming that that -1 is negligible. Okay, where is VBE? VBE is the voltage between the base and the emitter, right? So we'll call this VBE. Unlike basic circuit theory courses where we draw the dependent sources by a diamond, here we just draw them as a circle, as regular independent sources. That distinction is really not necessary when we draw these things because we know from the context, from the problem, whether this is dependent or not. So we don't bother with the diamonds anymore. Okay, so this is a voltage dependent current source, right? We have a voltage here. We have a current that depends on that voltage. It's a nonlinear dependent source, as you can see, but it's a dependent source anyway. Okay, that is the simplest bipolar transistor model you can think of. Why did I draw the current source from the collector to the emitter? Well, we know it has to come from collector because the collector is drawing that current, right? But should it be between the collector and the emitter or the collector and the base? Should I draw this current source this way instead of this way? Well, I cannot draw it to the base because I know that the base current is smaller. Remember that we said if the collector current is IC, the base current is IC over beta. Beta is maybe 100 or 200. So I can't do that. The only reasonable approximation or representation is to connect the current source between the collector and the emitter. All right, but something might be bothering you when you look at this, because we said previously that the collector and emitter currents are not exactly equal. They are close, but they're not exactly equal. Why? Because the emitter current contains the collector current and the base current. But here we don't see the base current. In fact, this is open, so there's no base current. So that's the problem. We have to fix that. All right? But the reason I drew it like this is that the first time you see a circuit with a bipolar transistor in it, your first reaction should be to think of the bipolar transistor according to this model. This is the simplest model. It has approximations. Now, after you understand what the circuit does using this model, you can make the model more complete in your mind. You can say, well, but there's a base current, so let's try to do something else, etc. That's the job of us as engineers. We have to start with the simplest model to gain a good understanding and some insight into the circuit, and then we replace that simple model with more complete models. All right, so how do I model the base current here? Well, remember we have an equation for the base current. We know that IB is equal to IC over beta, which is equal to IS over beta x of VBE over VT. This means that I am looking for some sort of device to place between here and here that draws this much current with this much voltage. It's a two-terminal device. One terminal here, one terminal here. And its job is to draw a current equal to IS over beta x bar VB over VT. Do we know any device that has this type of characteristic? It's a two-terminal device. When it sees VBE across it, it draws a current equal to the exponential of VB over VT multiplied by IS over beta. That's a diode. It's a PN junction, right? So why don't we place a diode between these two? So we place a diode here, and that diode draws a current. That diode happens to have a voltage across it equal to VBE right here. And it happens to draw a current equal to IS over beta times x bar VB over VT. Now when you buy a diode, what specification do you need to be able to calculate everything using that diode? We need IS, right? For diodes we had IS times x bar VD over VT. So I have to specify the reverse saturation current of this diode. How much is the IS of this diode? Well, it's this much, right? Because that's the equation for a diode. The equation for a diode says reverse saturation current times the exponential. It just happens that this has a reverse saturation current equal to IS over beta. So we'll just sometimes write it here, not all the time, to remember that the reverse saturation current of this guy is IS over beta, not IS, because the base current has to be this much, not this much. All right, so that is a more complete model. I emphasize that this model is true, is valid, only if the device operates in the forward active region. So that's important to remember. In forward active region. And forward active means the base emitter is forward biased, the base collector is not forward biased. Okay, so that's the model that we can use in various calculations. Congratulations. Now, any circuit that I give you that has bipolar transistors in it, you should be able to replace each transistor with this and calculate everything, solve the circuit. Because the circuit now reduces to techniques and topologies that we know from the past, or at least lends itself to simple KVLs and KCLs, etc. All right, that's a good start, and let's start from there and go through some examples to see what happens. Now, intuitively, you might expect that this exponential dependence this exponential dependence might give us some trouble in calculations. It's a nonlinear function. So let's see. Maybe it does, maybe it doesn't. Let me change the color of my pen, and we go and try something. So here's an example. Remember this little circuit here? We have a battery here, and a transistor here. All biased up in forward active region. We're happy with it. Now let me try to modify this slightly. So here's what I'm thinking. I have a battery here. I have a battery here. And I insert a resistor here. So we will call this V0. We'll call this R1. And this is VCE. And I will give you the values that I have chosen. So V0, I'm assuming it's 800 millivolts. Just as an example. R1, I'm assuming is 200 ohms. Again, just as an example. And IS of the transistor is 5 times 10 to the minus 16 amperes. Okay, and I would like to find the collector current, IC. All right, so we need to solve the circuit. We have a model for the transistor, so we can replace the transistor with this model and then solve the circuit and see what we get, right? Let me just double check my values here. Okay, I'm sorry, I actually assumed R1 to be 100 ohms. So let's erase this. All right, so we assume R1 is 100 ohms and these other values. Okay, so let's go ahead and replace it with a model. We can do it like this. So here's our V0. The model says place a diode between base and emitter. So here's a diode between base and emitter. Place a voltage-dependent current source between the collector and the emitter. Here's the voltage-dependent current source. Now, we happen to have a resistor from emitter to this point. So we have to add that here. Resistor between these 2 points. And then we have to have a battery from outside. So here's a battery, VCE. And we know the dependence of this upon this, right? So we know that if this is called VBE, then this is equal to IS XPOV. Well, I don't have room there. Let me try to erase this here and write it on top. So this would be IS XPOV VBE over VT, the value of this current source. So I replaced the bipolar transistor with its model. The model tells me what goes to what terminal. The diode goes between base and emitter. The current source goes between collector and emitter. That's all. Emitter is this point because that goes to the top terminal of R1. So now we have a simpler representation of the circuit over here. And we need to solve the circuit. Okay, and the unknown is this current, which is the same as this current, right? This current. Okay, this current is IS XPOV VBE over VT. So the unknown is VBE. If we know VBE, we know the collector current. Can I find VBE here? Well, maybe, maybe not. Let's make an approximation. So we assume that IE is approximately equal to IC, meaning that beta is quite large, maybe 50, maybe 100. So what this says is that this current, which is this current, which we call IE, is approximately the same as the collector current. The collector current comes down, and we don't lose much of it to the holes coming from the base. All right, or we don't get much contribution from the holes coming from the base. All right, so that current is IE. Which is equal to IC, approximately. Well, let's write a KVL around this loop. So KVL says that this voltage is equal to this voltage plus this voltage. This voltage is called VBE. We keep it like so. This voltage is equal to the resistance times the current through it. The current through it is IE, which is approximately equal to IC, as we saw. So we say V0 is equal to VBE plus R1 times IE, which is approximately equal to VBE plus R1 times IC. Okay. All right. Are we done yet? We are looking for IC. But we know V0 is 800 millivolts. We know R1, 100 ohms. But we don't know VBE exactly. We can make a guess, but we don't know it exactly, because VBE itself is a function of the collector current. So what I can do is, because IC is equal to IS x bar VB over VT, I can find VBE from here. So I can say VBE is equal to VT log of IC over IS, right? And I replace for VBE from here in here. So I can say this is equal to VT log of IC over IS plus R1 times IC. So now you begin to see the problem. We have V0, VT, IS, R1, and we are looking for IC. And this is a nonlinear equation that does not have a closed form solution. So how do we solve this problem? Well, if we have numerical values, as we do here, we can do it by iteration. So let me show you how we do that. Now for iteration, we try to have some term that includes IC on the left and some on the right. And I will write it like this. I will write V0 minus R1 IC is equal to VT log of IC over IS. R1 is 100 ohms, V0 is 800 millivolts, IS is 5 times 10 to the minus 16 amperes, and VT is 26 millivolts. All right, now to solve this by iteration, we make a guess for IC. Okay, and we plug it in there. We can either find this side based on our guess or this side. We prefer the weaker side, the weaker function. The weaker function is log, not a linear function, right? So we make a guess for IC, we find this side. Once we have this side, we can find a new value for IC. Now this new value becomes our new guess. We put it back in here, we find this term, we find a newer value for IC, and so on. So let's do that quickly, see what we get. So our guess is 1 milliamp. It has to be somewhat educated. You can't just make a really wild guess. You can't say this is 100 milliamps. Why? Because based on the numbers that we have here, 800 millivolts, etc., typical numbers, we know that this current is probably in the milliamp range. Now, you could make a guess of 100 milliamps. Nothing wrong with that. It just takes longer to converge to a reasonable solution. All right, so if IC is 1 milliamp, so I assume IC is 1 milliamp on this side. I plug it in here, calculate this. From here, find IC. This will give me a new IC. And that new IC comes out to be 0.636 milliamps. Now I plug this back into here. So this will give me some value, and from there I calculate the new IC, this new IC, and that will give me 0.753 milliamps. Now I use this, plug it in here, find this, from there find a newer value for IC, and that gives me 0.71 milliamps. 0.71 milliamps. So we see that we are gradually converging, right? We're gradually, so the actual current is probably somewhere between these two, 0.73 milliamps or something in that range. Okay, so we can continue this, but that's the procedure that we use for iterations. All right, so the purpose of this exercise was to show that because of the nonlinearity, the nonlinear function that we have here, and because we end up with an equation that does not have a closed form, we do have some mathematical labor. And you can imagine that once we have several bipolar transistors, the situation is more complex. Okay, now let's go ahead and look at another example. The next example will be very similar to this, except that I add a microphone above this battery. This system, this circuit has no signal. We have a DC here, no changes. But in reality, we should have some sort of signal coming in. We're trying to amplify it or process it. So let's assume that the signal is a microphone and is placed in series with V0. So remember that. We'll go to the next page. So let's add a page here, and we will redraw that circuit, this time with, let's see, this time we will redraw the circuit with a microphone in series with the battery. All right, so here's the next example. We have our bipolar transistor, and we have a microphone here, and the same battery as before, a resistor here, and another battery here. That's R1. This is V0. This is a microphone, and we know that the base emitter voltage is from here to here, and that's VCE. The purpose of these examples is to get comfortable with this model that we have created for the bipolar transistor and see how we can utilize it to solve circuits. Okay, so how can I modify the previous results to reflect the fact that now there is a microphone signal here? Well, let's assume some sort of time shape for the microphone signal. This signal, we will call it Vm for microphone sine of omega t, just a simple sinusoid. A microphone actually produces much more complex than that, but let's say it's just a sinusoid. Okay, so can I use the previous results here? Well, the voltage from here to here is equal to this voltage plus this voltage. This voltage is just V0. This new voltage is Vm sine of omega t. So I can say that this total voltage is equal to Vm sine of omega t plus V0. The rest of the circuit is the same as before. So if I go back to the previous page, I can readily see what needs to be changed. I simply go in here in this equation, and instead of V0, I write V0, the battery, this battery, plus the microphone signal, and the rest is the same. So we'll go and do that. So remember this equation, and we'll go to the next page and write it out. So let's see here. Okay, so we say V0 plus the microphone signal, Vm sine of omega t, minus R1 IC is equal to Vt log of IC over Is. Again, we are looking for the collector current in the circuit, and the only difference with respect to the previous example is that we have a sinusoidal microphone signal superimposed on the battery voltage connected to the base emitter. All right, so let's assume again we know R1, Vt, Is, and V0, and even Vm. How do we solve this equation? This is more complicated. In the previous case, IC was constant. It was like 0.7 milliamps, 0.72 milliamps, something in that range. But here, IC is a function of time. You see, this is a function of time, so IC ends up being a function of time. So what do I write? Can I assume that IC is a sinusoid? No, we don't know. This is a log, it's a nonlinear function. So what IC will be, we have no idea. Well, we have some idea, but it's more complicated. So the point of this exercise is to show that as soon as we bring in a signal, suddenly the analysis becomes more complex and sometimes quite prohibitive. And that's one issue with this type of model that we have developed for the bipolar transistors. All right, so that's somewhat disappointing. If this is so difficult, why don't we go to a simpler case first and see if we can handle that, and then try to attack these more complex cases. So let's do that. Here's another example. And I will remove this resistor, replace it with a wire, with a short circuit. So we go back to our simpler circuits, the things that we have seen in the past. So here's our microphone, here's a battery, and here's another battery, VCE. We have, again, the microphone signal is Vm sine of omega t. So there's really a voltage source that I just keep drawing as a microphone. And then, of course, our bias value, V0. And again, let's say we are interested in IC. So very simple. We don't even have a resistor anymore. So let's see if we can solve this circuit and how far we can go with that. And then later on, maybe we come back to that. Okay, can I find IC in this case as a function of time? This is constant. This is a function of time. I would like to find IC as a function of time. I will give you 90 seconds to think about it. All right, so what did you find? Well, this should be a little simpler than before. What we can say is that the voltage between the base and emitter, VBE, in this case, this voltage is just equal to this voltage plus this voltage. So we can say VBE of the transistor is equal to the microphone signal, or the battery plus the microphone signal. We have the bias value, and superimposed on that, we have the microphone signal. And we know that IC is an exponential function of the base emitter voltage. We couldn't do that before because the base emitter was not directly available in this KVL. But here it is directly available. So I can say IC is equal to IS exp of the base emitter voltage, which happens to be all of this divided by VT. So we have V0 plus Vm sine of omega t over Vt. So interestingly, we are able to find a closed form solution for IC in this case. Previously, we couldn't because of this resistor here. Okay, all right. Now, is IC a sinusoid if the microphone signal is a sinusoid? No, because we have exponential of a sinusoid. So the result is something strange. Now, if that's the case, in the general case, if Vm is any value that you want to choose, we say this circuit works under large signal conditions. We'll call this large signal operation. So this is an interesting and yet confusing term. Large signal operation means the following. Means that the signal that's coming to the circuit perturbs, sorry, let me just make it simpler. The signal that's coming to the circuit, the signal is arbitrarily large. That's all. It doesn't mean that it's large all the time. Sometimes it could be small, but it could be also large. That's why we call it large signal operation. Large signal operation means that this signal, which is coming from the microphone, doesn't have any limitation on it. Of course, as long as we are in the forward active region. So this signal could be some amount. V0 is how much? 750, 800 millivolts. How much is Vm? Vm could be 100 millivolts, 200 millivolts. We did not say Vm has to be small. If we don't have this limitation, if we don't say Vm is small, the signal from the microphone is small, then we say we are in the large signal regime. The large signal regime, that's what we have. We have IC as an exponential function of a sine, etc., relatively complex. Okay? That's what we call large signal operation. Obviously, there has to be a signal, because it's called large signal, and the signal may be large. Large compared to what? We'll have to see, but it's large. Okay, so we will now switch gears to what we call small signal operation, and let's see what that means. So, small signal operation. In the small signal regime, we make one assumption. The assumption is that the signal that is coming into the circuit is small. Small compared to what? Well, we'll see shortly. It has to be small compared to Vt, but that's to be shown. All right. So this means that the signal perturbs the bias, or what we call the operating point, by only a small amount. So before we go through this carefully, let me just give you the big picture here, the difference between large signal and small signal operation. So remember, IC is an exponential function of the base emitter voltage. So we'll draw that here. IC as a function of VBE. And what we have done is we have a microphone signal superimposed on V0. So the microphone signal is coming in like this as a function of time. Remember how we combined these two. So the exponential function looks like this. If this microphone signal perturbs the base emitter voltage, or more importantly, the collector current by a small amount, so you see it perturbs it by this much. When we are at the bottom of the sinusoid, the current is over here. When we are on top of the sinusoid, we are above here, over here. So if this current change is small with respect to the bias current, which is what we have in the absence of signals, we say we have small signal operation. So I repeat, if as a result of the signal going up and down, the change in the collector current is small compared to the bias value of the collector current, then we say we have small signal operation. On the other hand, we could not be in this situation. So let's draw using a different color, maybe this color here. So it could be that we are still around the bias, but then we have something like this. Now you can see that the current has huge fluctuations, the collector current, right? The collector current is here, then it's over here. So we have huge fluctuations. Then we are not in a small signal regime. So in small signal operation, what we do care about is that the bias conditions are perturbed by only a small amount, by a negligible amount. So this is a small perturbation, this is a large perturbation. Okay. All right, so let's continue this calculation now, assuming that we have small signal operation. And that means that I would like this term to be small. Now, does it mean that this term should be small compared to V0? No. It's actually more constrained than that. So let me write that here and see what we get. So IC is equal to IS exp of V0 over Vt exp of Vm sine of omega t over Vt. I just separated them. Now, what I would like to do is assume that this argument is much less than 1, because I know that exponential of a small number, so I know that e to the epsilon is approximately equal to 1 plus epsilon if epsilon is much less than 1. So I would like to use this approximation, which means I would like to assume that this term is much less than 1. And because sine itself is always less than 1 or equal to 1, I need to assume that Vm is much less than Vt. Okay, that's the key. Vm is not sufficient to be much less than V0. It has to be much less than Vt. So we assume Vm is much less than Vt, so that this argument is much less than 1. And I can expand it like so. So I can write IS exp of V0 over Vt 1 plus Vm sine of omega t over Vt. So where am I going with all of this? Well, hang in there, we'll see. Okay, what is Is exp of V0 over Vt? That says, if we have V0, V0 is here, right? Remember V0 is here, the bias value. We have Is exp of V0 over Vt. So, in fact, this term is the bias current of the transistor. The collector current of the transistor carries when there is no signal. There is only a battery voltage here, right? So we will denote this by something. We'll call it maybe IC0. That's the bias value of the collector current before we have any sort of signal on it. So then this would be equal to IC0. Let's bring this in. Plus IC0 over Vt times Vm sine of omega t. So now a lot of interesting things are happening here. Number one, we see that if this approximation holds, this approximation, right? Meaning if Vm, if the signal coming in is much less than Vt, suddenly the collector current that is drawn in the circuit has a sinusoidal behavior. Only this. Previously it wasn't like that, it was an exponential of a sinusoid, but now it's only a sinusoid. So that's interesting. So let's write that down. So in small signal operation, this is what we see. Number one, IC varies sinusoidally. Of course, assuming that the input is a sinusoid as well, right? If the input is a square wave, well, this will be different, right? Okay. The other point that we see is that this term, this factor here, IC0 over Vt, is a familiar quantity. What is that? That is the transconductance of the device. Remember, this is what we calculated last time. We said the collector current, the bias current, divided by Vt is the transconductance. So we can say that this is just Gm times that. So we have IC approximately equal to the bias current plus Gm Vm sine of omega t. That's fascinating, isn't it? That as soon as we made an approximation that the input sinusoid is small, the perturbation is small, the current is small, suddenly the output contains only a sinusoid, no more than that, and in fact that sinusoidal current is a current, right? It's a current. This current is just given by Gm of the transistor times the voltage, the signal voltage that's coming from outside, from the microphone. Gm, the transconductance, times the signal voltage from the microphone. Okay, so that's interesting. Now, graphically, this should not be very surprising. Here's what's going on. So again, if I draw ID versus VBE, we have an exponential function, and we are assuming a small perturbation. So here's our V0, and we are making a small perturbation here. Then this perturbation in the current, we are saying, is small and it's also sinusoidal, this perturbation here. So we see that this goes up here, this goes up here, and the current fluctuates between these two. So why is it that I can say that the output current fluctuation is equal to Gm times the input voltage fluctuation? This fluctuation is equal to Gm times the input fluctuation. So we're saying that this fluctuation, this voltage fluctuation, times Gm gives me this current fluctuation. Well, if this is very small, we know that delta V times the derivative gives us delta I, right? Because we know that derivative is equal to delta I over delta V when both delta I and when delta V is very small, right? So I can say that delta I is equal to delta V times the derivative, which we call Gm. So the voltage fluctuation times Gm gives me the current fluctuation. And that makes perfect sense. When we assumed that Vm was much less than Vt, in a sense, we are so small in this variation that we are looking at the slope of the curve. And the slope of the curve is Gm, so obviously the input times the slope gives us the output. The input change times the slope gives us the output change. And that's why we ended up here. So that's nice. All right. And yet one more perspective before we finish. Another perspective would be that in a sense I'm doing this. In a sense I'm assuming that the curve from here to here is a straight line, not an exponential. So if we take a piece of an exponential, if we take an exponential and pick two points that are very close to each other, we can approximate that by a straight line. So if this is a straight line and we give a sinusoidal function to that straight line function, we also get a sinusoidal function at the output. So small signal operation means that we are approximating the IV characteristic by a straight line only between 2 points. Okay, so we're only confined to this small variation of the current and this voltage, so we can use the linear approximation instead of the exponential function. All right, this is a quick view of the difference between large signal operation and small signal operation, and next time we will use this to develop another type of model for bipolar transistors. I will see you next time.